Hello everyone! In our new tutorial we will show you how to integrate the Nuitrack SDK with a Final IK asset. In this project we will control a robotic spider using body turns, as well as move two manipulators using our hands. Let's get started. For this project you'll need Nuitrack SDK from the official website, where you can also read the documentation, and the Final IK asset from the Unity Asset Store. Let's take the scene from the Final IK example as a basis. In this example, the spider can be controlled using the keyboard and mouse. We'll control the spider using our body tilts. Resave the scene so as not to change the original. There is a copy of the robot on this scene. We won't need it, so you can delete it. There are two scripts on the object MaxSpider and MaxSpider controller. Let's take a look at the second one in more detail. As we can see, there is a property in the script that returns an input vector, which is applied to the transform via transform translate. Transform is rotated in the direction of the camera. Also, this script is located in the specific namespace. To use the fields of the script, we will create our controller, inheriting it from MaxSpider controller. To do this, create a new script called Nuitrack Spider Controller. To get access to the original controller script, we will add a directive to its space in our script. We also added the inheritance from MaxSpider controller. The control will be described in the update method. So, how we will control the spider? To convert the body tilt, represented as a vector from the lower back to the head, to the input vector value from -1 to 1, we will use the vector 3-dot function. This function is similar to the cosine. It returns 1 if the vectors are directed in one direction and -1 if they are all directed in different directions. 0 means that the vectors are perpendicular. To determine the position of the head and lower back, we need to get the skeleton data from current user tracker. If the user is not in the frame, current user tracker returns null, so we need to check that the skeleton data are available. Now let's define the vertical direction of the user's skeleton as a vector from the lower back to the head. At this stage, it will be convenient to make a new method for the converted coordinates of the joints in the Unity system. The method takes the skeleton and the target joint type as arguments. Here we get the coordinates of the joint and convert them to a Unity vector using the 2vector3 method. Multiply them by 10 to -3 power, since Nuitrack provides the coordinates in millimeters. Now let's use our method to get the converted coordinates of the target joints, that is, the head and waist. Since it is a vector indicating the direction, it should be normalized. Let's define the vertical and horizontal values of our joystick axis, which is the skeleton, using the vector 3-dot function. As the first parameter, we will pass the vertical direction of the skeleton, and as the second, vector 3 back for vertical axis and vector 3 left for a horizontal axis. In the Nuitrack coordinate system, 0 is the sensor position, and the direction of the axis is similar to the direction of the axis for the Unity camera. If a user is facing the sensor and extends his arms forward, the Z coordinate of the arm will be less than the torso coordinate. We will also add a sensitivity rate to adjust the control sensitivity. Add multiplication by the sensitivity rate and limit the value from -1 to 1 using the method clump function. Apply the same changes to the horizontal axis. Using the received values, we will make an input vector. We pass the vertical as the x value and the z value as the horizontal. We leave the y value empty since the robot can't move up and down. The input vector value will be local for the robot's coordinate system. To get its value in the world coordinate system, we use the transform vector method of the current transform. This will allow us to get the correct movement and direction of the robot, regardless of its orientation in space. We don't want to depend on the transform scale in the coordinate system of which the conversion is performed, so we normalize the resulting vector and then multiply it by its length. Now let's move the transform using the transform translate method. As parameters, we will pass the movement direction multiplied by the speed, delta time of the current frame, and make spider scale so that the movement speed of our spider is proportional to the scale. Now let's move our script to the spider object and configure its fields like in MakeSpider controller. We'll leave the camera transform field empty for now and delete the old control script. We also need to set references to the controller script for the smoke and sand objects. To use Nuitrack, add the Nuitrack scripts prefab to the scene and enable the specified components. Let's check the control with the help of body tilts. Now set up the camera so that it always follows the robot and is correctly oriented. To do this, create an empty game object which we call camera center. Align its transform with the transform of our spider. Then make the camera object a child of the camera center object and set the desired position and orientation relative to the robot. We also need to remove the old camera controller script from the camera. In the camera transform field, specify reference to the camera center object. Set the camera control in the camera control method. Align the position of the camera center object with the position of our spider. The rotation is aligned only on the vertical axis. To do this, create a new quaternion angle axis. It takes the angle and axis of rotation as parameters. The camera control method should be called first in the update method. Let's run this scene and make sure that the camera follows the robot. To determine the skeleton rotations relative to the vertical axis, we can use the change in the shoulder position. Let's determine the direction vector from the right shoulder to the left. We also set the y coordinate to 0 to exclude the influence of the horizontal tilt. We calculate the quaternion of the arm's rotation using the quaternion look rotation method. As parameters, we pass the vector from the right shoulder to the left, as well as the vector of the vertical axis. We don't want to move the robot at the slightest change in the position of our shoulders, so we add a minimum angle of rotation. To calculate the angle between two quaternions, use the quaternion angle function. Before calculating the rotation delta, we define the quaternion of the shoulder's base rotation as if the user is standing straight in front of the sensor. This can be done in the same way, using the quaternion look rotation method. We pass vector of 3 left instead of the direction of the shoulders. To get a quaternion that represents the difference between the other two, we need to invert the base rotation and multiply it by the rotation of the shoulders. Since the quaternion is a matrix, the order of the operands is important. Now, to rotate the spider, it is enough to multiply its rotation by the delta of the shoulders rotation. But to make the rotation linear, we use the quaternion rotate towards method. As the first argument, we pass the current rotation of the robot, and the second one, we pass the current rotation multiplied by the shoulder's rotation delta. The maximum rotation degree for the current frame is defined as the product of the current frame's time delta and the rotation speed. Now we can run the example and make sure that the robot turns when the shoulders turn. To make our project a bit more interesting, we'll add manipulators to our robot. An example can be found in the Robotic IK scene. On this scene, the manipulator reaches for the target object using inverse kinematics. It is assumed that these manipulators will simulate the user's arms. To add a manipulator to our scene, copy the objects, open our scene with an example, and paste the copied objects. Set up the manipulator so that it moves in the local coordinate system. To do this, create an empty game object and name it tentacles. Then we make the manipulator object and the target children of the tentacles object. Align the manipulator position relative to the parent object. Now we can check our manipulator with the robot and adjust its size and position. There is a leg in front of the robot which will interfere with the manipulator movement, so let's delete it. We also need to remove the reference to this leg in MaxSpider. Let's create a script to control our manipulator. Like in the Nuitrack Spider controller script, we need to get the skeleton data in the update method. Now let's determine the position of the user's arm. To do this, we can use the function from the Nuitrack Spider controller script. We can just copy it here and use it. We will define the target joints for the current manipulator as a list. This will be convenient because in the future we will need data about the elbow to calculate the arm length. Since we will enumerate the joints in the list in order from the shoulder to the hand, the first operand in the vector difference should be the last joint, and the second operand should be the first one. Since the manipulator length and the user's hand length do not match, we need to get the normalized coordinates of the arm position. To do this, we need to divide the vector of the hand position relative to the shoulder by the arm length. Now let's define the method for calculating the user's arm length. To do this, we need to iterate the list of joints, each time adding to the total length the distance between the current joint and the next one. Add the division by the length of the user's arm. Now, before changing the position of the manipulator target object, we need to add a reference to it. However, the manipulator script is located in a specific namespace, so we need to add a directive to this namespace. This script that controls the manipulator is called fabric. Now we can access the target object of the current manipulator. Since the manipulator is controlled in the local space, we refer to local position. Now we multiply the more normalized arm position by the manipulator length. We also need to add a property to calculate the manipulator length. The algorithm of this method is similar to the algorithm of the method for calculating the length of the user's arm. We will go through the transform positions of the current manipulator components. Add multiplication by the manipulator length. Also, to make the movements smoother, let's add interpolation using vector3lob function. To do this, we will declare the interpolation ratio in the script fields. Let's change the target object positions of the manipulator using the vector3lob function. As the first parameter, we pass the current target position, as the second, the desired one, and as the interpolation value, we pass the time delta of the current frame multiplied by the interpolation ratio. Move the script to the tentacles object, add a reference to the fabric scripts of the current manipulator, and set a list of shoulder, elbow, and hand joints in hand joints. Make the tentacles object a child of the body object. Now let's create a prefab in order to easily configure the manipulator for the second hand. Change the manipulator position and update the list of joints corresponding to the second hand. Let's run the scene and make sure that the manipulators work. If you want to use ready-made prefabs from the Nuitrack tutorial, you need to add a Final IK value to the scripting defined symbols. After that, the scripts of this tutorial will become available. That's it! Now you can use this project as a reference for animating other avatars with inverse kinematics in Unity. As we can see, the Nuitrack skeleton data allows you to animate even characters that do not look like humans. Thank you for watching this tutorial and see you next time. Bye!